In this tutorial, we are going to focus on strategies for solving solution stoichiometry problems. And so we're just going to take a look at a couple of examples that deal with I would say, a couple different variations of solution stoichiometry problems. Note that these aren't all of the possible problem types that you will see, but this will hopefully give you some strategies for dealing with this type of problem. So taking a look at the first example and just highlighting some of the key ideas. So we've got 50 milliliters of a 0.20 molar solution of sodium sulfate, and that's being combined with 80 milliliters of 0.10 molar of the lead 2 acetate. And we're told that a white precipitate forms. So we need to, in this case, identify the precipitate and then calculate the maximum mass of the solid that can be collected. And so our first job definitely is to determine the precipitate. And so I write down the formulas for each of the reactants. And this is why the work that we did early in the course with nomenclature is important, because notice you weren't given the chemical formulas. You need to know those at this point. And so I've got the chemical formulas for each, and it's a double displacement reaction happening. And so I write down the two possible products, and then take a look at my solubility guidelines and recognize that my precipitate has to be lead 2 sulfate. And that's important because along with all of the information that's given in the problem, I need the molar mass of my precipitate in order to find the maximum mass of the solid that can be collected. And so one other thing about the given information, just note that it was given in milliliters, but I converted these values to liters, holding on to the appropriate number of significant digits. And of course I'm converting to liters because my concentration values in the 0.20 molar or moles per liter involve liters. So here, just as before, I kind of lay out my game plan. This is how I'm going to go about solving the problem. And so I start with the concentrations of each, and I need to find the number of moles of each. And the reason why I have to convert to moles is because eventually I'm going to have to, in order to find the number of moles of my precipitate, the lead 2 sulfate, I need to determine which one of my reactants is the limiting reactant. And so once I determine the limiting reactant, then I can get the number of moles of PbSO4 that would be formed, and then of course use that molar mass value that I indicated up here to find the mass of PbSO4. And so number one is laid out here. I want to find the number of moles of Na2SO4, set things up so my units cancel out, and we get this. And I do the same thing for number two and finding the number of moles of the lead 2 acetate, and we get this. To determine the limiting reagent, in this case, it's actually relatively easy. I mentioned that we have a 1-to-1 ratio, and if we take a look at the balanced chemical equation, for every 1 mole of Na2SO4, we need 1 mole of of the lead 2 acetate. And so, since those two things are in a 1-to-1 ratio, the lead acetate is the limiting reagent, and that's quite simply because there are less moles of it than there are of the Na2SO4. And so then I can use the number of moles of PbSO, or to determine the number of moles of PbSO4, I can quite simply say that they are equal to the number of moles of the lead 2 acetate, because once again, the PbSO4 is in a 1-to-1 ratio with that lead 2 acetate. And so, right again, that highlights the importance of having that equation properly written out and properly balanced. So now that I know my number of moles of the lead 2 sulfate to be 0.08 moles, I can use that number of moles to figure out the mass, the number of grams of the lead 2 sulfate, and I get 2.4 grams. And note that I have two significant digits because in some of my initial numbers I had two significant digits given here and here, and three significant digits given here and here, and based on the operations that we did, we were only allowed then in the end to have the two significant digits. And so I summarize that in a statement. And in terms of a check, sometimes for these stoichiometry problems, there isn't necessarily an obvious check or a check that could be kind of concisely written, and so for that reason, I don't state a specific check here. But certainly, if there's something that you can think of that is relevant to the problem, by all means include it. So in this next problem, this is a little different in that we are already told that our precipitate is barium chromate. So we don't have to determine that, but what we are asked to determine is the concentration of barium ions in the solution, given that we have 50 mils of 0.15 molar barium nitrate and 50 mils of 0.12 molar potassium chromate. And so once again, like we do for all solution or for all stoichiometry problems, is we write the balanced chemical equation, and then I just wrote all of my given information beneath the appropriate substances. And so I've got for the barium nitrate, the potassium chromate, and then I know that in the end I'm trying to find the concentration of Ba2 plus ions in moles per liter. And so what that means is that I'm probably going to have to find the number of moles of the barium chromate to allow me to eventually find the amount of Ba2 plus ions that are left, and I'll explain more down below. One point or one other piece of information that will be helpful, if I'm looking for the concentration of barium 2 plus ions in that final solution, I'm going to need the final volume, which is just the addition of the 50 mils and 50 mils for 100 mils. So once again, the basic game plan is the exact same that we've seen before over and over again. So I need to take those concentration values and convert them to moles, and I do that in both cases. I then need to determine what my limiting reagent is so that I can eventually find the number of moles of the barium chromate, which again is my precipitate. But now here's where things get a little different, is I need to somehow use the amount of barium chromate that I had produced to see how much barium or how much Ba2 plus was left in the solution. And so what that kind of indirectly tells you is that between these two reagents, the barium nitrate has to be the excess reagent, and the potassium chromate needs to be the limiting reagent, because we are told that there are some barium ions left in the solution, and so this has to be in excess. And then after I get the number of moles of Ba2 plus, I should be able to calculate the concentration of Ba2 plus using the fact that I know the final volume will be 100 milliliters. And so again, quickly take you through number 1 and number 2 when the number of moles are calculated. That's fairly straightforward. In number 3, I'm just further justifying here that the limiting reagent is in fact the K2CrO4. Again, we see that there's a 1-to-1 ratio between the two reactants right here, and the number of moles of the K2CrO4 are less than the BaNO3, right? So there's less moles of this stuff than there is of this stuff. Therefore, the potassium chromate has to be the limiting reagent, and so it's going to determine the number of moles of the barium chromate. And again, it's because those things are in a 1-to-1 ratio that I don't need to use a mole ratio to find the amounts, right? Because the potassium chromate right here is in a 1-to-1 ratio with the barium chromate, so the limiting reagent is in a 1-to-1 ratio with the item that we're interested in. Then it's the number of moles of potassium chromate is quite simply equal to the number of moles of the barium chromate, which is this value here. But here's where it takes a turn. From this, I need to find out how many moles of barium are left, or how many moles of barium remain in the solution. And so to do that, I'm going to take the number of moles of Ba2 plus that were initially in there and subtract the number of moles of Ba2 plus that were used. The number of moles of Ba2 plus that were present initially are quite simply equal to the number of moles of barium nitrate that was present in the initial solution. And because these two things are in a 1-to-1 ratio, it's the same as the value I calculated up above, right? Because when this BaNO3 when it dissociates, you get basically 1 mole of Ba2 plus and 2 moles of the nitrate. And so since the amount of Ba2 plus produced is the same as the, or is in a 1-to-1 ratio with the BaNO32, the number of moles are the same. The number of moles of Ba2 plus used is just equal to the number of moles of the barium chromate precipitate that were produced. And that was the value that was calculated up here. And again, it's because everything is in a 1-to-1 ratio that holds true. And so I can subtract these two values and get the number of moles of Ba2 plus that are left to be 1.50 times 10 to the minus 3. And then I can use that value along with the total volume to find the concentration of Ba2 plus in that solution. And a quick check here would be that the concentration of Ba2 plus is that remains in the solution is smaller than that initial concentration of BaNO32, because of course we know that some of the Ba2 plus from the BaNO32 was used to produce the precipitate, the barium chromate. So again, hopefully you see that this is still stoichiometry. Stoichiometry is stoichiometry. The big difference being now that in solution stoichiometry, we're dealing with concentration values as given information and volume as given information instead of maybe masses and that type of thing. But ultimately, the strategy is still find the number of moles. The first thing you need to do is find the number of moles, and then, based on what the problem is asking, go from there. Probably then use the number of moles to find a limiting reagent, and then solve in the appropriate format. So stoichiometry is still very much stoichiometry.